In final exam review part 2, we're going to take a look at some probabilities. In problem 1, we have that in a class of 10 girls and 12 boys, a 5-person committee is to be formed to talk about the prom. Answer the following. How many total committees can be formed? So we're talking about possible combinations. We want to use our combinations formula, which is N choose R. So remember, N is the total amount and R is the amount you're choosing from. So if we're looking at a total of 10 girls and 12 boys, that's 22 people, and we want to choose 5 of them exactly to form our committee. Now remember, this is a function in your calculator, and for most calculators, you want to go to alpha, window, and then 8. If you don't have this function on your calculator, please let me know and I can tell you how to do it on yours. So when I do 22 choose 5 in the calculator, we're going to get 26,334. So that's how many total committees can be formed. In B, we want to know how many committees could be formed that contain 2 males exactly. So out of the 12 boys, we want to choose exactly 2 of them. Then that means that of the 10 girls, we have to choose 3 of them. And then we're going to multiply those two combinations together to give us 7,920. Lastly, how many committees could be formed with all female? So that means of the 10 girls, we're going to choose exactly 5 of them to get our committee, which gives us 252. Notice how B and C were asking for how many committees and not what's the probability. If I wanted to find the probability in either B or C, I would just take the value I got for how many committees and divide it by how many total committees can be formed. And that would give me the probabilities of getting a committee with exactly 2 males and the probability of a committee that's all females. We're actually going to take a look at how to calculate a probability in number 2, where we want to know the probability of getting 3 of a kind in poker. So for the probability, we have to set up our fraction. The denominator is your total possible outcome. So there are 52 cards in a deck, and we want to choose exactly 5 of them, because in a hand of poker, you have 5 cards. If we're thinking about how to get 3 of a kind, out of 13 cards in each suit, I'm going to choose 1 of them because I want 1 card from each suit to give me 3 that are the same. And there are 4 suits. So the 4 times 13 choose 1 is going to give me my 3 of a kind. Now the remaining 2 cards, they can't be anything that was similar to one of our 3 of a kind, because then it could either be 4 of a kind, or if those 2 remaining cards were the same, I would have 2 pair. I would have a full house, which we don't want. So of our remaining 12 cards in the deck, we want to choose 2 of those. And then we want them to be different. So that's where we're going to have 2 different 4 choose 1. Because I don't want, of those 2 cards, I don't want them to be the same. So plugging this into our calculator, we're going to end up with 88 over 4165, which is about 0.0211. So you have about a 2% chance of getting a 3 of a kind in poker. In problem 3, we're going to take a look at the binomial distribution probabilities. And these formulas will be given to you on your exam. Make sure you're looking at that final review formula sheet so when you're comfortable with those formulas. So we have that there's a 32% chance that randomly selected female likes to dress in yellow. If 10 people are randomly selected at large from the population, answer the following. So what is the probability that exactly 2 of them will like to dress in yellow? So when we're finding a probability, we use the formula N choose R times P to the R times Q to the N minus R. So N choose R comes from our different combinations that 2 people would like to dress in yellow. P is the probability of success. Q is the probability of failure. So for our specific example, of our 10 people, we're choosing 2 of them. The probability that exactly 2 of them would like to dress in yellow is 0.32 squared. And then I have to take into account the probability that the rest of them don't like to dress in yellow. So 1 minus 0.32 is going to give us 0.68. And then when I do 10 minus 2, we're going to get to the 8th power. So when we type that in a calculator, we're going to get 0.2107. So there's about a 21% chance that exactly 2 of our 10 females like to dress in yellow. In B, we want to know the probability that at most 3 of them would like to dress in yellow. So there's 2 options you can go here. We can go the route of finding the probability of 0 of them, plus the probability of 1, plus the probability of 2, plus the probability of 3. That's going to be the longer route because I have to do 10 choose 0 and then the whole formula. Then I have to do it for 10 choose 1, 10 choose 2, 10 choose 3 and add them all together. Your other route is to use your summation formula. So we're going to have the sum from x equals 0 to 3. Then we would do 10 choose x. And in parentheses we would have 0.32 to the x times 0.68 to the 10 minus x. To get to the summation part in your calculator, you're going to do alpha window 2. And again, if your calculator doesn't have that alpha window function, please let me know and I'll help you figure out how to get the summation. In both cases, no matter how you choose to do it, you should get the probability of 0.5956, which is roughly a 60% chance. So there's about a 60% chance that at most 3 of them would like to dress in yellow. Finally, in C, we want to know the mean number of females who would like to dress in yellow. So the mean for a binomial probability distribution is found by doing n times p. So the number you have times the probability of success. So in this case, that's 10 times 0.32, which is going to give us 3.2. But because we're talking about people, we can't have a decimal, so that basically becomes 3 females. Next, we're going to take a look at some z-scores. So these are the most basic z-scores. So we're going back to the very beginning in chapter 7 when we introduced the concept of the standard normal probabilities. So we want to know the probability a randomly selected individual will have a salary of over $60,000. So if we're looking at how to calculate a z-score on our formula sheet, z-score equals our value we want, so 60,000 minus the value, your normal value, which is 56,789 over 4, 5, 6, 7, which is the standard deviation. So we're talking about the average salary of a politician and their standard deviation. It's normally distributed. So if I'm looking at the graph of this, my normal curve, over 60,000 would be the top. So we have our normal 56,789, our mean, with the value we want, 60,000. So calculating the z-score, remember for z-score, always round to 2 decimal places. Once I do this math in my calculator, we're going to get 0.70. At this point, I'm now going to go to the standard normal, our z-chart. I'm going to find 0.70. And because we want to be over 60,000, I have to do 1 minus the probability for 0.70, which is 0.7580. And when I do 1 minus 0.7580, we're going to get 0.242. So there's about a 24% chance that a randomly selected individual will have a salary over 60,000. In B, we want to take a look at the probability a randomly selected individual will have a salary between, and I'm going to change this 40,000 to 42,000 and 50,000. In this case, when we want to be between two values, we have to calculate two z-scores, one for each of our values. So I'm going to start with the 42,000 minus 56,789 over the 4567. After I do it in the calculator, we're going to get negative 3.24. For our second z-score, we're going to do 50,000 minus 56,789 over the 4567. And that's going to give us negative 1.49. Now we need to find both of their probabilities using our z-chart and then subtract them. So for the negative 1.49, we're going to get 0.0681 minus, and for negative 3.24, we're going to get 0.0006. Once we subtract those two values, we're going to get 0.0675. So almost a 7% chance that a random individual would have a salary between 42,000 and 50,000. In our last example, we want to know what salary we would need to earn to be in the top 10% of all salaries for politicians. So that means if I'm looking at my curve, if I want to be in the top 10%, that means 90% of people have to fall below. So we're going to use this probability to find our z-score. So when you go to your z-score, you want to find the closest value to 90%. And that z-value is 1.28. We're now going to use our known z-value and set it equal to the equation we used in A and B to find that x value. So we're going to have 1.28 equals x minus our mean, 56,789, all over our standard deviation, 4,567. My first step is going to be to multiply both sides by that 4,567, which again is going to give us 5845.76 equals x minus 56,789. Then we're going to add that 56,789 to both sides to give us a mean salary of 62,634.76. So that is the salary you would have to make in order to be the top 10% of all salaries for politicians. In number 5, we're going to take a look at our geometric distribution. So we have that there's a 13% chance that a randomly selected person has a dog, and we want to find the following probabilities. So in A, we want to know the probability that the first person you talk to that has a dog is the fifth person. So the formula for finding the nth success in the first trials is P times Q to the n minus 1, where again P is the probability of success and Q is the probability of failure. So probability of success is going to be 0.13 times the probability of failure. So when we do 1 minus 0.13, we get 0.87, and because we're talking about the fifth person, it's going to be 5 minus 1 in our exponent. Evaluating this in a calculator, we're going to get 0.0745. So about a 7% chance that the first person we talk to that has a dog is the fifth person we speak to. In B, we want to know how many people on average you will have to talk to until you find a dog owner. So the mean for a geometric distribution is found by doing 1 over P. So 1 over the probability of success, which in this case is going to be 1 over 0.13, which gives us 7.69. And again, can't talk to a decimal of a person, which means on average we would have to talk to 8 people. Last problem on part 2 says a box has 30 tickets in it, 1 with a 5 on it, 2 with a 4 on it, 1 with a 3 on it, and the rest with a 1 on it. Construct a probability distribution for the number on the ticket, then compute the expected value of the number on the ticket. So when we're constructing our probability distribution, we set up a table. And our table has to contain our outcome, x, and its probability, p of x. So in this case, we have 4 different outcomes. Our outcomes are that we could have a ticket with a 5, a 4, a 3, or a 1. The probability is how many of those 30 tickets have that number. So there's 1 out of 30 with a 5, 2 out of 30 with a 4, 1 out of 30 with a 3, and then the rest, so when I do 30 minus 1 minus 2 minus 1, we end up with 26 out of the 30 have a 1 on them. So this is our probability distribution. The expected value is the mean. So in order to calculate the expected value, we have to take each outcome, multiply it with its probability, and add them together. So we're going to do 5 times 1 out of 30 plus 4 times 2 out of 30 plus 3 times 1 out of 30 plus 1 times 26 out of 30. Multiplying each of these values by their probability and adding them all together, we're going to get an expected outcome of 1.4, which makes sense since the most number of tickets came with having a 1 on it. So you would expect that to be your expected value, something close to the most amount of tickets. Please let me know if you have any questions over anything covered on final exam review number 2.